Hello, and welcome to my lecture, part of the GROWTH Astronomy School on Observational Techniques for Transient Studies. This lecture follows up on my previous lecture on basic optical image data reduction to introduce a few additional advanced techniques or corrections that may be necessary for certain types of images in certain circumstances. While it won't be needed to take part in the practical exercises that are coming up as part of the summer school, you may nevertheless find it useful to read through these slides and listen to this lecture in case you do encounter situations where you need one or more of these techniques, as is likely if you continue on with your studies in optical transient astronomy. At the end of the previous lecture, I showed this slide mentioning a range of additional techniques or steps that may be needed for certain types of observations. Masking bad pixels, dark subtraction, linearity correction, charge transfer correction, sky and fringe subtraction, dealing with cosmic rays, and solving for astrometric distortions. I will briefly go through all of these in this supplementary lecture, although I won't describe any of them in great detail. The first correction that you may find necessary for certain circumstances is to deal with bad pixels and bad columns. These are very common in CCDs and other gridded detectors of all types due to a variety of circumstances. You may have dead pixels, such as the one here, which have either greatly reduced sensitivity or no sensitivity, such that they always read out only the bias level and actually contain no signal at all beyond that. You may have hot pixels that produce signal even if there is no photon flux incident upon them. And you may have bad columns or charge traps, which either produce continuous signal and that signal flows out along the whole column, or stop any signal that flows through them. In all of these circumstances, you'll have a significant number of pixels in your array which are not usable for science and only contain garbage data, which ideally should not be used. While if you dither your telescope properly and collect a large number of observations of the field and are careful in keeping your source of interest far from any of these defects, this may not necessarily be necessary. But if you're only taking single observations, you may have to correct for these effects. The way this is done is relatively straightforward. Because these patterns do not change from exposure to exposure, if you take calibration data appropriately or science data and simply look through it carefully, you can identify each of these pixels in various ways and flag them and store them in a mask table. Then by looking up those mask values, you can note during your observations which pixels should not be used in science data processing, either by setting those pixels to not a number values or explicitly sending the mask to the median combination software to make sure that they are completely excluded from further processing. You may also replace the pixels with the values of nearby pixels if you're confident that this will not compromise scientific measurements. The next topic I'll talk about is dark current. I did mention this in my previous lecture as an effect that is usually not important in the optical, but can be important in the near infrared. I demonstrate this here with a couple of infrared exposures, both of which were taken with the shutter closed, and as a result, there's no signal coming in from outside the instruments. In a 1 second exposure, there are 24,000 counts readed out in each pixel value, but in a longer exposure, that number has gone up dramatically to 180,000 counts. This is a very large amount of signal that must be removed prior to flat fielding or any other step of processing. The way we deal with this is simply a generality of the bias frame. Instead of an overall bias frame that you apply to all images, you acquire dark frames that are customized with the exposure times that match those that you collect in each science image. So if you have 10-second science images, you acquire 10 seconds dark images. If you have 60-second science images, you acquire 60-second dark images. And then you produce a median combined dark frame with those dark images and subtract that from the science images as needed. I'll talk next about linearity. As I mentioned in the previous lecture, good CCDs tend to be linear until you reach the saturation point where they no longer collect any signal and read out the saturation value, regardless of how much additional flux that you have on that pixel. However, not all detectors may have this property. You do have some detectors where, while linear up to a certain point, after that point, you have slightly fewer counts than you would expect given the overall gain ratio of the CCD. This is an example of nonlinearity. To measure this and determine if it's important and if you need to correct for it, and then come up with the procedure for how to correct for it, we acquire a series of special calibration exposures by setting a flat lamp to constant illumination and then taking exposures with varying exposure times. We then check if the number of counts is proportional to the exposure time in each image. If it isn't, we can model this and rescale up our higher count pixels in each image appropriately. While most CCDs are good to 60,000 or at least up until 50,000 counts, most astronomers do prefer, just in case, to keep their science relevant counts for important observations and for their flat field calibrations in particular, around or below about 30,000 counts, just in case there are additional nonlinearities that weren't noticed. Most good CCDs also have very good charge and transfer efficiency. Charge transfer efficiency says how accurately, when a charge is accumulated in a pixel, that charge is then moved all the way to the amplifier and does not get stuck or left behind. But this doesn't always happen, particularly for detectors that are in space, such as on the Hubble Space Telescope, and exposed to high degrees of radiation flux. The pixels can get damaged. And as a result of this, electrons can actually get left behind during the charge transfer step and not make it to the amplifier in the same pixel that they started out with. This is not a straightforward thing to correct for, but it can be measured and it can be used to apply a correction across the array depending on the flux and depending on the position of each pixel to move charge that was stuck and left behind from the pixel that it was measured in to where it should have been in. It usually isn't necessary for ground-based observations, but if you deal with observations from HST, very likely during your data processing, the software that you use, which is usually customized for that instrument, will include a charge transfer efficiency correction. These tend to be biggest for pixels that are far from the amplifier and lowest close to the amplifier, which is usually why in HST, unlike in ground-based images, the source will be placed near a corner as opposed to in the center of the image. Again, this is difficult to do, but usually the HST scientists will provide software that allows this to be done for you. In contrast, one other effect that you will encounter from the ground and can be very important is fringe correction and sky subtraction, which are related steps that need to be done for observations for which the sky is particularly bright. This arises from the fact that while we do flat fielder observations to remove pixel-to-pixel variations, the pixel-to-pixel variations in quantum efficiency are in fact a function not only of the pixel, but also of the wavelength. And the wavelength that we use for the light to take our calibration images, whether that be dome flats or whether that be twilight sky flats, has a different spectrum and therefore a different central wavelength from the background sky that is underlying our actual science measurements. As a result, all of these differences between different pixels may not be completely removed and require an additional correction step to provide a truly flat sky background in our science observations. This tends to get worse the further into the red you go. For optical detectors that are observing in the nearest part of the infrared, such as the I band and the Z band, up to about 1 micron, this can usually be done as a single step that is called a fringe correction. Further into the infrared, this becomes much more serious. And in fact, even between different exposures of the night sky, the sky itself is changing in spectrum, requiring even more detailed corrections. An example of fringe subtraction is shown here. On the left, I show a bias subtracted image, which shows a clear, broad scale pixel-to-pixel differences, which are a result of interference patterns between the wavelength of the light and the pixels themselves, because they tend to have similar sizes. The flat field is shown in the middle, which interestingly does not show the fringe patterns, because unlike the skylight, the flat field light is from an incandescent lamp with no lines, but the skylight comes from a series of strong emission lines called air glow, which leads to these strong interference effects. And as a result, these interference patterns are not corrected out by the flat field and remain in your science image. And this will greatly limit both the depth and the accuracy of the measurements of faint sources. The solution to this is we median average many nighttime exposures to produce a sky frame. So after we've done the flat correction, we do an additional correction that essentially produces an additional separate flat field based on the night sky, very similar to the super sky flat method I described before. And we subtract that out of our observations of the field. Blue word of about 1 micron, we only need to do this once for the night. We can essentially median stack all the exposures that we got in that filter, combine them together, and subtract that with appropriate scaling from our science observations to remove the fringe pattern. Further into the near infrared, because the sky spectrum is changing rapidly with time, essentially we need to construct a custom sky frame for each image by medianing the images that were collected near in time to it. So an example of this is shown here. At the left, we show a flat fielded image similar to the one I showed before, which contains the fringe pattern. In the middle here, I show a fringe frame, which is taken of a large number of images like this that were all median combined together to remove the stars. And at right, I show the result where the fringe pattern has been almost entirely removed. CCDs detect not just light from photons, but they also detect electrons that are coming from other sources because they are fundamentally electron detectors and only indirectly photon detectors. These can originate from charged particles that strike the detector, which can come both from terrestrial radioactivity, radioactive elements in the detector and the telescope, and also from energetic particles entering from outside the atmosphere called cosmic rays. These are not easy to distinguish just by looking at the detector, so astronomers tend to call both results cosmic rays. They look at like strange patterns like this, curls, straight lines, single clusters of pixels that have large amounts of additional signal relative to surrounding pixels and are not blurred by the atmosphere like true astronomical sources are. That lack of blurring is what allows us to detect them in individual images and remove them as necessary. There are a variety of algorithms that people have developed to look for these sharp features using edge detection and other sorts of techniques and identify those pixels and either mask them similar to the first part of this lecture or replace them with values of nearby pixels to average over them, which can allow them to be combined with other exposures without having to rely on medians. One should always be very careful when doing this forever because these algorithms do not always solely remove the cosmic ray fluxes, but can actually remove real astronomical signal if you are not careful, and seeing conditions are different compared to what you might have expected. So always be careful when running these sorts of algorithms and visually check that the results are reasonable. An additional correction that is often needed to the astrometry is to deal with nonlinearities in the solution. Only the simplest, smallest field detectors are purely linear all the way from the center through the edges. Almost all real telescopes, and in particular wide field telescopes, have additional nonlinear terms due to distortions in the shape of the detector and in the optics of the light that is focused onto the detector. Depending on what you're doing, you may not need to correct for these because you may only be interested in a single object like a supernova in the field, as is usually the case in time domain astronomy. But if you are mosaicing together several images to produce a larger field, for example, or you require precise offsets between sources near the edge of the image and those in the center of the image, you may need to correct for this effect by solving for a more complex model with additional terms. There are various software packages to do this, as it is normally quite complicated mathematically to do on your own. Unfortunately, there is no single standard for representing these distortion parameters in fits, unlike the case for simple linear solutions. There are different rival models, and different types of software may be able to interpret some of them, but not others. So this is another case where the user should always be aware that you are using a consistent method for storing and interpreting these astrometric distortions. Most astronomers will rely on advanced software packages to do this, but you should always be careful when running them, because if the model that is being used is either too complicated or not complicated enough, this can actually make the astrometry worse than it is in a linear solution only. So always be careful. And always be aware of, because the result of these different conventions, some software may not be able to interpret the solved image that you produce. So again, always double check that these terms are actually being applied before relying on this for your science. When you're stacking distorted or rotating images together, or even if you just want to deal with subpixel effects, you will need to actually resample the images to a common pixel grid rather than the simple shift and add method introduced in the previous lecture and used in our tutorials. So for example, if you're adding two images together with different rotations, you can't simply line them up. You actually have to resample both of these images onto a common grid, as shown here in this example, by setting a new pixel grid, usually with the same pixel scale, but a different orientation and a different center than the input individual pixel grids. By translating each pixel in the original grids to a pixel on the new grid, we can then combine them in the usual pixel average method to come up with our final stacked image. There are various ways to do this and a variety of algorithms that are designed for this process. You can use simple nearest neighbor, which is not the best way, linear interpolation, quadratic, bicubic, and many other algorithms to do this simple resampling and interpolation method. The most common software package for doing this is called Swarp. It's very easy to run and very effective. Be aware, though, that when you do this, this can change the background noise properties of your image because you are averaging some pixels together in different ways than other pixels, depending on how many pixels go into the averaging. This is fine for images that are well sampled across the PSF, such that an astronomical source is actually being smeared across many different pixels. However, if you're dealing with an observation where things are undersampled, such as images from HST or images with very, very good seeing from the ground, this may not quite be simple enough. This oversimplified method may not be adequate for your data, and special algorithms may be needed to recover information on these scales, rather than simple interpolation. The most common and longest used algorithm for this is called Drizzle, and you can look at this paper here for the details on how it works. The advantage of methods like this is that you can actually recover information that is smaller than the scale of individual pixels by using multiple observations together to infer subpixel structure. The last thing we might want to do in our observations is to photometrically calibrate the image and not just establish the different pixels on a relative flux scale as flat filtering gives us. This usually isn't necessary because it tends to be better to do this together with a photometry in the next step of data analysis for imaging, which you'll hear about in the next lecture. However, one thing to be aware of is that if the transmission is changing during the course of an observation, such as if clouds are moving in and out, you may need to actually calculate the photometric scaling of each image individually before you combine them together. That's all I have to say. Note that you don't have to do every one of these steps every time. And indeed, you may not need to do any of them for the simplest types of instruments and the simplest forms of data processing, depending on your science goals. Again, as I said earlier, the key is to understand your instrument and to understand your science needs so you know which steps are essential and which are not. Always be suspicious if at the end of the result of your process you get images that look wrong and have variations in the sky levels between different parts of the field, or have stars with strange shapes and strange PSFs or other effects. If you do, you may need to do different corrections. Thanks once again. And as a reminder, all these materials, both the lectures and the tutorial content, will be made online, available to the general public at the end of the school. Thanks again.